Hi, this is video for task 2, conceptual exploration. To me, beyond school experience is basically that tutoring is only special because we provide stuff that school can't provide the students with, right? At school, you are sharing the resources with maybe hundreds of other students, probably not hundreds, but less than 100 of other students, but still quite a lot, right? And the teacher obviously can't make the learning experience unique for you, right? It has to be general for the whole class. So maybe you won't get the best experience at school. Whilst at tutoring, you are special. We provide personalized teaching for you. And so that makes the learning much more easier for you because it's designed for you. So it's beyond school experience. And learning to understand also very fundamental thing that I also believe, a fundamental principle, because if you just try to memorize concepts, most likely that you won't be able to solve the harder complex questions or even questions with just a small tweaks. Yeah, if you just try to memorize. Whereas if you do, if you try to use intuition and to understand the concepts, then you can solve questions that's not the exact same as in the textbook, right? And that's maybe modified a little, right? Premium service, what can I say? At Contour Education, we have excellent tutors, excellent resource, and excellent tutors with experience. What can I say there? So I think that's what it is. So we'll move on to the tasks. Right. Exploration 1. How do the complementary relationships for the circular functions, again, trig functions, sine and cosine work? This is actually done in task 1. So I'm just going to briefly talk through the first method. I've done 2 methods here. First method, again, we can draw a right angle triangle with 2 angles, x and 90 minus x. So considering this angle x, sine of x is just opposite of hypotenuse, which is O1 divided by h. Cosine is A1 divided by h. Right. That's just year 10 stuff. Now looking at this complementary angle 90 minus x, sine of 90 minus x is O2 over h, opposite over hypotenuse. So O2 over h. Well, what's O2? Can you spot what does O2 equal to? Well, it is just A1, right? O2 and A1, they are the same side. And what's A1 over h? Well, that's just what? That's just cosine of x. Yeah. A1 over h. Similarly, we can do cosine of 90 minus x. Cosine is adjacent to hypotenuse. So we have A2 divided by h. Right? Again, what's A2? Well, A2 is O1. So we have O1 over h, which is sine of x. So these are our relationships, complementary relationships between sine and cosine. Yeah. It's called complementary because the 2 angles, they add up to 90 degrees. Yeah. So that's one way of thinking about these relationships. Let's look at another way, from another perspective. Let's look at the graphs. Okay. So just for now, focus on the blue curve. Focus on the blue curve. So we have a normal sine function f of x equals sine of x. Right. Domain, not domain. Yeah, domain 0 to 2 pi. So frequency is 1. Yeah. Okay. And here we went from 0 to 4 pi. So we have 2 cycles. Wow. Now consider if we shift this sine curve, sine wave, by pi on 2 units for 90 degrees to the left. So here, before it was here, now it's here. So then we have this black curve. So the black wave is the shifted version of sine. Right? Oh, can you spot something? If you only look at this period, let's look at here. Let's start from here. Let me go here. That looks like a what? That looks like a cosine function, right? We keep going, another cosine wave. So just by a shift, or even without a shift, you can think of it as a cosine function, right? This is the cosine function, just shifted. Yeah. So in a way, we can conclude that cosine is just the shifted version of sine, and vice versa. So sine and cosine, they're just shifted version of phenomena. As you can see here, sine of x, we can just shift it, and we would obtain that event, cosine. Okay. Right. Next up, this we are looking at the change of base law for logarithms. This is actually a typo. It should be log of x to the b divided by log of x to the a. Right. So that's the correct that. To show you why this is true, let's think about what logarithms actually do. It essentially answers this question. To what power must the base be raised by to obtain the given number? Okay. So for logs, we have a base and we have a number inside the bracket, right? So to what power does the base need to be raised by to obtain the given number? That's what log is trying to answer. So for example, in our question, log of base x to a is the same as to what power must x be raised by to obtain a. Similarly, log x to the b is to what power must x be raised by to obtain b. Log a of b, log base of a to b is to what power must a be raised by to obtain b. Yeah. Now suppose log of x to the a equals y1, right? We just let it equal to y1. Log x to the b equals to y2, and log of a to the b equals z. We'll just define those three terms. Then by definition, x to the power of y1, what's that equal to? A, right? Because we need to raise x by y1 to obtain a. Okay. That's the definition of logs. So x to the power of y1 is a, and similarly, x to the power of y2 is b. And a to the power of z is b as well. Yeah. Now, let's look at x to the power of y1 divided by x to the power of y2. This is a over b, right? A over b. But using index law, this is just x to the power of y1 minus y2. Now we can rearrange b to the other side. So we have a equals b times by x to the power of y1 minus y2. Now we can replace this b with a to the power of z, as in here. Replace b with a to the power of z. So you have a equals to a to the power of z times by x. Well, y1 minus y2. What's y1? y1 is log x to the a. y2 is log x to the b. Okay. y2. So we have this. Then on the exponents, log of x to the power of a minus log x to the b, or using simple log law, that's just log x to the a divided by b. Yeah, simple log law. And again, using log law, this, think through the logic here. X to the power of log of x, or to the a over b, is a over b. Yeah. Because log of x gives you what power do we need to raise x by to obtain a over b. And that's that power. And now we actually raise it to that power. So of course we would obtain a over b. Yeah. So then we have a to the z times by a over b. Well, we have an a on both sides. So we just divide by a. We get 1 equals a to the z divided by b. Rearrange b equals a to the z. Therefore, we can take the log. Log of a to the b equals z. And that's proved. That's the right-hand side, right? Log a to the 12, log a to the b. Right-hand side equals to z. Well, what's this again? What's this equal to? Log of a to the b, we can replace a and b. Before we said a is x to the y1 and b is x to the power of y2. So let's replace it. So we have log with the base x to the y1 to x to the y2. Now we can use a log law. We will move y2 down, right? So we have y2 times by log base x to the y1 to x. Okay. Well, what's log x of y1 x? This is answering the question, what power do we need to raise x to the y1 by to get x? All we see the answer is 1 over y1, right? If we raise x to the y1 by 1 over y1, then by index rule, we would get x. So this log expression is the same as 1 over y1. So we have, again, so we just have y2 over y1. Well, what's y2? Y2 is log x to the b. Y1 is log x to the a. We have log x to the b divided by log x to the a, which is equal to log a of b. And that's the proof. Okay. So this is a mathematical proof. Maybe it's not a very rigorous proof, but it's just to show you why this is true. Yeah. And I hope you can understand it from the inverse relationship between exponentials and logs. Okay. They are inverse to another. Okay. Let's move on to the next one. How can we understand the formula to find the volume of revolution for a function around the x-axis? Okay. The formula is volume equals integral from a to b pi times by y squared dx. Y is basically the formula, f of x. So let's consider this curve. It's just a general curve, right? So curve y equals f of x. And we are looking for between a and b, x equals a and x equals b. Okay. Suppose we have some point x, and that has a corresponding y. Now let's increase x by delta x. So small increments, delta x. Okay. Then obviously the corresponding y value is y plus delta y, right? It's some delta y, or some delta y. Okay. Now just consider this highlighted part. If we rotate that around the x-axis, what would you expect? You'd probably see something close to a cylinder, right? Close to a cylinder, but not quite, obviously, because the increments here. Close to a cylinder with height. What's the height? Well, the height will be this. The height will be this, right? That will be the height. So the height is delta x. What's the radius? That will be the radius. Yeah. Think about a cylinder. Radius y. Right. So we approximately have this cylinder with radius y and height delta x. And this will be even closer to a cylinder as we move delta x to 0. As we take the limit of delta x to 0. So we are decreasing this increment. Now, what's the volume of a cylinder? It's pi r squared times by height, if you remember from year 10 and year 9 geometry. So volume of cylinder is pi r squared times by h. So the volume for each small disk, which is this, let's call it delta V. What's that? That's the volume of a cylinder. So we just sub it into the formula. Pi remains pi, r squared, r is the radius, so y squared, h is the height, so delta x. Okay, so we have that. Hence, what's the total volume? Well, the total volume is just summing up these small disks right? We're just summing up these small pieces. So that, we just sum them all up. Right? So we do. So the volume is the sum of the volumes. But we take the limit as delta x goes to 0, right? Because we want it to be close to a cylinder. Yeah, so we need to move the increments close to 0. So we take the limit outside of the summation. Okay, so what's delta v? We'll replace that with the formula we did above, pi y squared delta x. Okay, now what do we have? We have a limit of a summation. And what's that? Remember that this would just be integration, right? Remember that integration is just the sum of small things. That's what integration is doing. Here we have a sum, and limit gives us the small things. So we have a sum of small things. So we end up with this integral a to b pi y squared delta x, which is the increments, then becomes dx. And you can see this is the formula we have about. Right. So this is the formula for the volume of a revolution around the x-axis. Okay. And you can do the same sort of stuff if you're doing revolution around the y-axis. Yeah. Okay. Next up, we have conditional probability. This formula, probability of A given B, is probability of A and B divided by probability of B. Why does this make sense? Let me draw you a Venn diagram. Suppose we have this diagram. This is the set of sample space, the set of possible outcomes, so omega. And we have event A, event B, right? And obviously here, that's the intersection, A and B. So what's the probability of A given B? That's the probability of A occurring, given that B has already occurred. So B here is a certain event. Therefore, we are in some way restricted to looking at these highlighted parts only, because B must have happened. So we are somehow restricted to only looking at this area. Right? So we can only look at this highlighted part. Now, under this condition, we want A to occur. What's the only possible way? Will be A given A and B, right? The only possible way is the events A and B under this condition. So what's the probability of this event under the new sample space B? You can sort of think this condition as saying B here is the new sample space, right? Obviously, it's not the actual sample space, but we can sort of think of as a new sample space. So what's the probability of A and B happening under the new sample space B? Well, you can think of it in terms of area. This is what we want, and this is what we have. Okay. So then we can ask the question, what proportion of B is A and B? And then it's simple. A and B divided by B. Okay. Finally, we can find the probability, being probability of A given B equals probability of A and B divided by probability of B. Right? Lastly, we have to look at the binomial distribution formula. Okay. So first, what does the binomial distribution answer? It essentially answers the question, in n trials, what's the probability of getting exactly R successes? Recall that. Right. So before we move on to that n trial sort of stuff, let's look at a single trial, a Bernoulli distribution. A Bernoulli distribution has two outcomes, success or failure. Success with probability P and failure with probability Y minus P. Suppose we have n of those trials, n independent and identical Bernoulli trials. So we have trials 1, 2, 3, blah, blah. Each trial could be a success or a failure. Yeah, success or failure. My question is, what is the probability of getting R successes? If I want R successes, what's the probability? Well, we just get the probability of success, P, raised to a power of R. Right? But are we there yet? No, because we want exactly R success. We don't only want R successes, but we want exactly R successes. Right? In other words, we also need the rest to be failures. So we need N minus R failures. So what's the answer now becomes? We not just need the probability of success, but we also need failures, N minus R failures. Are we done yet? No. Why? Because each trial could indeed be a successful trial. We have N trials here. Each of them could be success, and each of them could be a failure. So in other words, we have different combinations of getting R successes and N minus R failures. So the question now becomes, how many combinations do we have? Well, if you did combinatorics stuff, you will know that the answer is N choose R. Out of N trials, we choose R successes. So N choose R. Putting them all together, we have this formula. N choose R times by probability of success, R successes, and N minus R failures. Formula. Okay. This is the end for video 2, task 3.